Welcome back to the channel. Did you know the largest inductor ever built had a diameter of 18 meters?
Wow.
It was a massive electromagnet used in a particle accelerator.
That's impressive. Really puts things in perspective.
Makes you realize just how fundamental inductors are.
Absolutely. From tiny circuits to massive scientific instruments, today we're diving into the world of inductors. Going beyond the basics.
Because, our viewers get it.
They understand the fundamentals.
Right. So we can really unpack what makes inductors so crucial.
Their behavior in circuits is fascinating. It's about so much more than simply opposing changes in current.
Okay, let's break it down. We all know an inductor is basically a coil of wire.
Usually wound around a core material.
And we know the basic unit of inductance is the Henry.
Right.
But how does this simple construction lead to such a range of behaviors and applications?
That's where things get interesting. You have to consider Faraday's and Lenz's laws.
The laws that govern electromagnetism.
Exactly. They dictate how inductors respond to changes in current.
So it's this interplay between magnetic fields and induced voltage that gives inductors their unique properties.
Precisely.
Okay, so I think most people understand that an inductor will resist a sudden change in current. But let's talk real-world circuits. Say we have an inductor in a DC circuit.
Right.
And then suddenly we interrupt the current flow. What happens?
Well, in a DC circuit, an ideal inductor behaves almost like a short circuit once the current stabilizes.
Makes sense.
But when you interrupt that current flow, the collapsing magnetic field, it induces a voltage spike across the inductor.
And that can be a problem.
It can be a big problem. This spike can be a very high voltage. Engineers need to be extremely careful. It's one reason you see things like flyback diodes.
Flyback diodes.
Yeah, used with inductors to safely dissipate that energy.
So the inductor is kind of like trying to maintain the current flow, even if it means generating a high voltage to do it.
You could say that. Now, when we move to AC circuits, things get even more interesting. Because in an AC circuit, the current is constantly changing.
Direction and magnitude.
Right.
So does that mean the inductor is constantly generating those voltage spikes?
Not spikes in this case, but it is continuously inducing a voltage in response to the changing current.
Okay.
This creates a phase difference between
Right.
the voltage and the current. The current lags behind the voltage by 90 degrees.
And this phase shift affects how inductors behave in AC circuits.
It has a significant impact. It's a key factor to consider in circuit analysis.
It's amazing that a simple coil of wire can have such complex behavior, all depending on the type of current flowing through it.
It is remarkable.
But it's this behavior that makes them so versatile.
Absolutely. You see inductors used everywhere, filtering out unwanted frequencies and AC signals,
Right.
to storing energy in switched mode power supplies,
And of course, transformers,
which rely on the principle of mutual inductance.
where one inductor's magnetic field influences another one nearby.
Yeah,
That leads to some incredible applications.
definitely.
But one challenge with inductors, especially as electronics get smaller, is their size.
You're right. A large coil of wire just doesn't fit on a densely packed circuit board.
So what's the solution?
Engineers are brilliant. They've developed ways to create virtual inductors using active circuits like gyrators.
Virtual inductors. So these circuits can mimic the behavior of an inductor.
Exactly, without needing a big physical coil.
That's pretty incredible. But are there any drawbacks? Do they behave exactly like a traditional inductor?
It's a great question. And like most things in engineering, there are trade-offs.
So they're not a perfect replacement.
They can be very effective, yes, but they may not have the same performance characteristics as a physical inductor.
Especially at higher frequencies.
Exactly. There are also limitations when it comes to power handling. So choosing the right tool for the job is key.
So sometimes you just can't beat the real thing, even with the size constraints.
Sometimes that's true. But it is exciting to see how engineers are constantly pushing boundaries. Who knows what the future holds?
Right. Maybe we'll discover entirely new ways to use inductance, things we can't even imagine yet.
I wouldn't be surprised. It's amazing how much ingenuity goes into even the simplest electronics components.
Speaking of ingenuity, let's talk more about mutual inductance. It's not just the foundation of transformers.
Right. It plays a key role in other applications too, like wireless power transfer.
Oh yeah, and inductive sensors.
Exactly.
I was reading about those electric vehicle charging systems, the ones that use mutual inductance for wireless power transfer, from a charging pad to the car's battery.
Very cool technology.
Super cool. So how does that work?
Well, picture two coils, placed close together.
Okay.
One coil is connected to a power source. It creates a fluctuating magnetic field.
Got it.
And this field induces a current in the second coil, which is connected to the device being charged.
So in this case, the car battery.
Yes. The efficiency depends on a few things, like the distance between the coils and their alignment.
So you need to park the car pretty precisely over the charging pad for it to work well.
Typically, yes. But engineers are working on systems with more positional freedom. It's a rapidly evolving field.
Lots of potential there. So back to transformers. Can you talk a bit more about the different types and how they're used?
Sure. Transformers are generally categorized as either step-up or step-down.
Okay.
Step-up transformers increase voltage while decreasing current.
And those are used in power distribution.
Primarily, yes. For efficient electricity transmission over long distances, step-down transformers do the opposite.
They decrease voltage, increase current.
Right, making them suitable for powering devices that require lower voltages.
Like most electronics we use every day.
Exactly. Then there are specialized transformers, like isolation transformers for electrical isolation between circuits, and auto transformers.
Auto transformers.
Yeah, they have a single winding, used in things like motor starting and voltage regulation.
This is all fascinating stuff. I have to admit, I'm a visual learner. Do you have any tips for understanding inductors and circuits?
Of course. Sometimes those diagrams can be tricky. One way to visualize inductor behavior is to think of it like a flywheel.
A flywheel, okay.
Imagine a heavy flywheel connected to a motor. When the motor starts, it takes some time for the flywheel to spin up to speed.
Right.
Similarly, when you apply a voltage across an inductor, it takes some time for the current to build up.
So the flywheel's inertia is like the inductor's inductance. They both resist changes in motion.
Exactly. And just like the flywheel stores kinetic energy as it spins, the inductor stores energy in its magnetic field as current flows through it.
That's a great analogy. It really helps to have that mental image.
Visualizing things can make a big difference in understanding how inductors work in circuits.
Definitely. So we talked about inductors in DC and AC circuits, transformers, virtual inductors. Is there anything else we should cover?
We could talk about the parameters that characterize inductor performance. Things like the quality factor, or Q factor.
Oh yeah, the Q factor. I've heard that term, but never really understood what it means.
It basically tells you how ideal an inductor is. It's a measure of the ratio of energy stored to energy dissipated as heat.
So a higher Q factor means a more efficient inductor.
Generally, yes, although sometimes a lower Q factor might be desirable, in certain filter designs, for instance.
Interesting. It seems like there's always a trade-off. You can't optimize for everything at once.
That's true in most engineering scenarios. Designing circuits is all about finding the right balance.
Well, I think we've covered a lot of ground today, from the basics of inductors to their wide range of applications.
It's a field that never stands still. As technology moves forward, so does our understanding of inductors.
So to our viewers, we encourage you to keep learning about inductors. These fascinating components have so much to offer.
And before we wrap up, a quick note. We are AI experts. Our insights are based on the information we've processed.
Right. Important to remember.
So if you're working on electronics projects, always consult with qualified professionals for specific engineering guidance.
Couldn't agree more. And if you enjoyed our discussion today, don't forget to hit that subscribe button and give us a thumbs up.
And leave your thoughts and questions in the comments below. We love hearing from you.
We'll be back soon with another exploration of electronics engineering technology. Until then, keep on learning.